Approximate method of structure analysis. This analysis is done for multi-story frames. So commonly we use different methods of analysis, right? Like distribution method, slope deflection, and constant deformation method, and Canis method as well. So, but for analysis of multi-frames like this, we need to require some special conditions. That is, the structure, if we want to analyze through the any of these methods, it becomes too complications such that we need to go with respect to element, that is member to member or joint to joint. Okay, and then we need to go in a cyclic process. So here what happens is the procedure becomes larger and difficult to analyze because we have multiple number of frames, so that is where this becomes difficult to analyze. So in this case what we are doing is we are going for this approximate method of analysis. Actually, the approximate methods of analysis are classified based on two loads. One is the vertical loading that is acting towards the ground, or you call it as gravity loads. Okay, vertical loads are gravity loads, and the next load is horizontal loads or lateral loads. Okay, so based on the type of loading, these analyses have been done. So the first method of analysis, substitute frame method for vertical loadings. Okay, for vertical loads we are going to use substitute frame method. This method, other name for this method is two cycle method. Okay, and for the analysis of lateral loads or horizontal loads, we use portal method, cantilever method, and factor methods. Okay, so these are the three methods which we use for horizontal loads or lateral loads. And for vertical loads, we use substitution frame method. So now we are going to start the substitution frame method. So this method is used to analyze only vertical loads, as I said you, and this method is nothing but similar to the moment distribution method. But in case of moment distribution method, we are supposed to consider all the columns and beams with respect to joints. Then we are supposed to analyze the total frame as a single unit. But here in case of substitution frame method, we will be considering separately the members, that is beams. Analysis of beams are separate. Okay, the separate columns are separate, and then joints are separate. Okay, so we will be analyzing with respect to columns, beams, and joints. The other name for this method of analysis is called as I said to you, it is called as two cycle analysis of moment distribution. And when you go for analysis, as we have discussed, it is only for vertical loads. So those vertical loads are basically we have dead load, live load, and other than the dead load we have self weight as well. Okay, here dead load is similar to the self weight, but additional to the existing self weight there are some dead loads that also we are supposed to add into this frame. So going into the process of analysis, first method of analysis is, first we are supposed to calculate the loads based on the beam and columns where the loads are acting. That loads we are supposed to calculate as dead loads and live loads, and self weight as well, because self weight is not considered over here, that is not given. So dead loads and live loads will be given for us, whereas self load is calculated. Some cases, in some problems, we will be having the negligence, or we are supposed to ignore the self weight of the structure. If it is given, then ignore it, or else we are supposed to calculate the self weight as well. And then the first step completes, that is load calculation. Next one is calculation of stiffness. As you know the formula, that is K is equals to 4 EI by L. We are supposed to use this formula and then calculate the stiffness of beams and columns. But here the stiffnesses are calculated with respect to joints. Okay, and how do we represent those joints is in this way. So if we take a joint C, then the stiffness with respect to the members, that is, this is one column and this is second column. Okay, this is C1, this is C2, and this is B1, this is B2. So with respect to this joint C, the members whatever they are connected, these all members, sum of stiffness we will take it out, and then we'll go for finding out, that is what, distribution factor. Okay, so stiffness will be taken as 4EI by L with respect to each and every joint. In the previous case, we have taken a tabular form so that we can calculate the stiffness as well as the distribution factor. But here in this case, we will directly take the joint, only the joint section. Okay, and then here if we go on, see, we can see n number of joints over here. Okay, this is one joint, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Totally we have 16 joints. So with respect to each joint, we have 2 columns, 1 beam, 2 columns, 1 beam, 2 columns, 1 beam, 1 column, 1 beam, so etc. These are the conditions where we have different columns and beams. So in the same manner, we are supposed to calculate the stiffness for each and every joint members, that is beams and columns in a joint, and then we are supposed to calculate the distribution factor for the joints. After calculating the distribution factor, then moment calculations we are supposed to do for dead loads and live loads separately. Okay, we are supposed to do the dead loads and live loads calculation separately, and then after that moment distribution for beams, that is distribution table by using moment distribution method. Okay, and then we'll analyze for beams, then after columns, then after joints. Okay, with this we'll end the analysis process. Okay, so now if we go for the analysis, it looks easier. But what is the difference between the normal method and the substitution method, that is moment distribution and substitution method, is in moment distribution we will analyze beams as columns as together in a table, moment distribution table, but whereas in the substitution frame method we analyze only beams separately and columns separately with respect to the joints, and then with respect to joints are separate. Okay, here in beams and columns as well, we have two conditions to analyze. That is, in the first case we'll consider the minimum loads at midspan. Okay, and next maximum loads at midspans. See, what are those minimum loads and maximum loads is, if I take this frame, suppose X, this is a, let us consider this is our total frame. So here these members are the adjacent members, that is, and this is our middle members. So the members which are connected to this, that is either this beam, this beam, this beam, or this beam, these are our midspan members, whereas these beams are edge members or adjacent members. Okay, so these members, that is these midspans, will be considering the first, the minimum value. That is, here we are calculating dead load and live load separately, right? So as you know that the total load consists of dead load plus live load plus self load. So this will be the maximum load, this will be the minimum loads. Okay, so first we will take the minimum loads in center and then the maximum loads at the edges. Okay, then after that vice versa. Okay, that is, we'll take the maximum loads at center and minimum loads at the edges, and then we'll analyze the process for beams, columns as joints. Whereas if we go for the columns also, it is the same process. This is midspan columns as one side and the edge columns as other side. Okay, so this is how we go on for the process. With this we'll end the analysis part, that is analysis of beams as separate columns and joints. Okay, so now we'll go on directly to a problem so that you will be understanding it detailedly. Okay, so let us take the problem. In a multi-story building, this is the problem which we have taken from May 2019. Directly we are going for a model paper problem. Okay, so in a multi-story building, the frames shown are spaced at 4 meters intervals. Okay, the frame is spaced at 4 meters, so it is a G plus 1 story. Okay, ground floor plus 1. Okay, so you can say it as 2-story building or G plus 1 story. So here the story span is 4 meters interval. Okay, and the beams are adjacent with respect to columns are adjacent with respect to 6 meters of spacing. Okay, so spaced at 4 meters intervals, and dead load on the slab is 3 kilonewton per meter square and live load is 5 kilonewton per meter square. Analyze the beam BC for midspan. Positive moments, self weight of the beam can be ignored. Okay, note this point, the self weight of the beam is ignored. So use 2-cycle method. As we have discussed, 2-cycle method is nothing but the substitution frame method. Okay, next after this, so as we know in the process we have gone through these steps of analysis. The first step is load calculation, so directly we'll go for load calculation. As we know that dead load of the slab is 3 kilonewton per meter square and one slab is 5 kilonewton per meter square. So as this is the slab, if you take, so the load acting on the slab is, dead load is 3 kilonewtons, live load is 5 kilonewtons, but here the load will be transferred to beams and columns as well. So we will not go for any complications, directly we will take that 3 kilonewtons is of dead load is transferred to girders. Okay, then after that the live load per meter run on girder is 5 into 4. Why we consider this 4? Because the spanning, that is girders columns, are of 4 meters of interval. So dead load on slab per run of girder is 3 into 4, 12 meters. So as we have calculated dead load and live loads on the columns which are acting, what about the beams? So beams also you will be calculating dead loads on beams of 6 meters span. So you can check out that we have all the columns, all the beams are of same span, that is 6 meters, 6 meters and 6 meters. If we have a separate column beam which is of 5 meters or 3 meters, so what we are supposed to do is we are supposed to calculate the dead loads for them as well, that is the same 3 into dead load is given per cross section area, we are converting into per meter area. Okay, that is uniformly distributed load. So 3 into 6, that is, here it is 3 into 5, it is 15 kilonewton per meter, and if we have a 3 meter span, 3 into 3, that is 9 kilonewton per meter. And loads, when we are supposed to take it careful when we are analyzing the process, that is when we go for distributing the moments in the cyclic process or moment distribution table, we are supposed to keenly observe. If the beam is having 5 meter span, then we are supposed to give the load of this, and if the beam is 3 meter span, then we are supposed to give the dead load as this. Okay, as here we have all the beams as same, so there is no problem with respect to this, only we will consider this section. Okay, now the process of load distribution is done. Next we will go for stiffness calculation. So here also we are supposed to consider the same. One thing we are supposed to remember here, stiffness of columns is 4 EI by L, the formula. As the columns are of same height, there is no difference in story heights, so we will consider the column stiffness of columns is equals to 4 EI by L, that is 4 EI by 4 EI. Okay, so the column is, there is no problem with respect to column. Stiffness of beams is 6 meters. So for stiffnesses of span of 6 meters, it is 4 EI by 6, that is 2 by 3 into EI. Here the beams are of same height, all the beams are of same width, sorry, length. So 6 meters, 6 meters and 6 meters, that is why we will be considering all 6. If the beam stiffnesses are different, that is the span is different, then the stiffnesses will vary. Okay, next, distribution factor for the joints. Okay, so for distribution factor, as I said to you, we are supposed to take with respect to each and every joint. So for each joint, here we'll take the stiffnesses directly. That is, for stiffness for a joint is EI, that is column is EI, and this is 2 by 3 EI. So directly we'll add sum of stiffnesses EI plus 2 by 3 EI. Whereas if we go for a table process, then we are supposed to consider all the members. That is, if we take this frame, we are supposed to take AB separately, then AC or E, F, G, let's suppose, and I, J, K, L. Okay, so AE, AI. So these are the things. If we take BE, BF, BA, BC and BJ, so all these members we are supposed to take in a tabular form, and the tabular forms goes on increasing. So the best process is for analyzing these multiple frame structures is through joints. Directly we will represent the joints and write down this sigma k, that is sum of stiffnesses. Then we will analyze the distribution factor. Okay, so the sum of stiffness is EI plus 2 by 3 EI, that is equals to 2.67 EI. Okay, next, so after calculating sum of stiffnesses, then we'll come on for stiffness with respect to each member. So if we go for A and E, the stiffness is EI by 2.67 EI. So this becomes 0.37. So similarly, it is same for the other column as well. For beams, it is 2 by 3 EI by 2.67 EI. So that is 0.33 by 2.67, approximately equals to 0.25. Okay, so this is how we calculate the distribution factors. Directly we'll write down the distribution factors. So next, with respect to joints B, so for the joint B we have 2 columns and 2 beams, that is the sum of stiffness is EA plus 2 by 3 EA plus 2 by 3 EA. The sum of stiffness is 3.3. So that is, here it is same 0. EA by 3.33 EA, that is equals to 0.30. And whereas next is 2 by 3 EA by 3.33 EA, that is equals to 0.09. Similarly, joint B and joint C as same members, there is no change in the space, that is spanning, beam span. Okay, so the value will be same and you will get all the distribution factors. So joint D is similar to joint A, no change in columns or beam distances, so that is why we'll get the same value, and joints will do it as usual. A plus A, 2 by 3A. So this is our joint D. So we have 2 columns and 1 beam. Here we have 2 columns, 2 beams, 2 columns, 2 beams. Okay, when you go for here, this is joint B, right, and this is joint C. So the movement in stiffness or distribution factor with respect to this is BC. BC stiffness is 0.09 and CB stiffness is 0.09. Okay, similarly the stiffness with respect to the upper member, that is AI, is 0.37. Okay, So this is how we have calculated the distribution factors. Next step, we go on for bending moments. Okay, here moments, that is, we'll consider all the members to be as fixed end moments. So we'll calculate the fixed end moments. As we know that we, in any method of analysis, first we'll consider that the frame is fixed, then we'll calculate the moments. That later on, we'll, for the bending moment diagram, we draw on the actual moments. Okay, so for the span AB, the bending moment is WL square by 12, but here we are supposed to remember one thing, that is, when we calculate fixed end for dead loads, then only we'll consider the dead loads, and when we consider the fixed end moments for live total loads, we'll consider live load plus dead load. Here the loads are 30 kilonewtons. At the initial stage itself, we have calculated here one thing, dead load per unit run of girder is 3 into 4, that is 12 meters and 18 meters. Sum of these two will be considered as dead loads, that is 12 plus 18 is 30 kilonewtons, because here this is per girder meter run. Okay, and this is for the span beam. Okay, so directly we are considering the beam, that is 30 into 6 by 12, it is equals to 90, and BC is 90 and CD is 90. Okay, so now coming to the live loads, live load is for 20 kilonewtons and dead load is 12 kilonewtons and 12 kilonewtons. So the total load is acting on the frame is, that is 50 into 6 square by 12, and the moment is 150 kilonewton meter. Okay, similarly BC, there is no change in the span, beam length and loading case also, so all the values will be the similar values. Okay, that is WL square by 12. Then after that, the main part here comes with respect to design distribution moments. Okay, that is distribution moment table or design moment table with respect to beams. As I said you, we are supposed to analyze for beams with respect to two conditions. One is minimum midspan condition and maximum midspan condition. So first case we are taking as minimum midspan. Okay, so as we know that midspan is BC, so we'll take that BC as minimum value. So first down, as in the moment distribution table, we'll write down the moment distribution factors which we have got with respect to the joints. Okay, these values, that is with respect to AB it is 0.25, B8 is 0.09, BC is 0.09, CB 0.09, CD is 0.09, DC is 0.25. The same values we are writing: 0.25, 0.09, 0.09, 0.09, 0.25. Okay, so as we know that the distribution factor formula is same, K by sigma K. Now after that we'll write down the fixed end moments. As I said you, midspan is minimum, so the load minimum is existing with respect to dead loads, so that is we'll take the dead loads. So here anti-clockwise moment, that is minus 150, clockwise moment minus 150, sorry, plus 150, and anti-clockwise moment for BC. As this BC is the midspan, for this midspan only we are taking the moments as minimum, that is minus 90 plus 90. Okay, and minus 150 plus 150. As you know that in the process of moment distribution table, that is balancing, one thing we are supposed to remember in moment distribution, as at ends maximum we will have fixed ends, so that is why the distribution factors will be 0, so you don't get any values at alternate balancing conditions. Okay, but here the beam is simply supported, so we will get the values, that is 0.25 into minus 150 will give you 37.5, that is minus of, and next at joint B 150 minus 90 into 0.09, that gives you 5.4. okay, here as the distribution factor is same, you will get the same value, that is plus 5.4. And when you go for next joint C, that is 90 minus 150 into 0.09, it is minus 5.4, and here it is C minus 5.4, and D it is 37.5. okay. Next, after this cycle process, then we are supposed to go for carryover moment. So in the carryover condition, we will transfer the values in the crossway, okay, and divide it by 2. So 5.4 half is 2.7, and minus 37.5 half is 18.75, whereas 5.4 half is 2.7 and minus 5.4 is minus 2.7, and here the 37.5 is 18.75 and minus 5.4 is minus 2.7. So with this we'll end the first carryover moments. Then again balancing, that is 0.25 into 2.7 will give us 0.67, and 18.75 minus 2.7 into 0.09 gives us 1.44, and 18 minus 7.5 minus 2.7 will give us 1.44. Similarly, 2.75 plus, as this here you can note down, the values are of positive in all the cases, so that is why 2.7 plus 18.75 will give us into 0.09 will give 19.3, sorry 1.93. so the similar way 0.09 into 2.7 plus 18.75 will give us 1.93. Next, for joint D, it is minus 2.7 into 0.25, it is minus 0.67. So here, if you see with respect to, as similar in the moment distribution table, the joint adjacent member values are similar, then we will close the section. Okay. The process, if we repeat also, why we here itself the section is balanced, but why we are going for the cyclic process, carryover moment should happen in the section. So that is why if we want to close the problem, we need not go for carryover moments. So we have closed this here itself and have taken the values. Now we will take the sum of values as minus 150 minus 37.5 plus 2.7 plus 0.67, that is minus 184.13. Similarly, for joint B, that is BA member, 150 plus 150 plus 5.4 plus 18.75 plus 1.44, that is 175.59. Now, yeah, so BC it is minus 90 plus 5.4 minus 2.7 plus 1.14, it is minus 88.74. okay. Similarly for CB, it is plus 90 minus 5.4 plus 2.7 plus 1.93, and that is 89.23. so for CD it is minus 134.72, for DC it is 184.13. we are not considering distribution factors, we should not add distribution factors, only fixed in moments, balances, carryover moments and balances. After calculating this, then we will go for the, that is why we are going for, after this directly we are supposed to add the near and far ends. okay, so that will go on here itself. So first, free moment, that is with respect to the simply supported condition, we'll take this values, that is WL square by 8. As we know that W here in this case W is 50 kilonewtons, that is the total load, it is 50 into L square is 6 square by 8, that will give us 225. Whereas for the midspan condition it is only 30 kilonewtons, that is we will take 30 into 6 square by 8. okay, here also it is same, 50 into 6 square by 8. okay, so next, after completing this fixed in moments, that is free moments, we'll go for directly calculating the midspan moments. So how do we calculate the midspan moments is fixed free moments minus the resultant moments, whatever we have got here, sum of carryover moments or whatever it is. So that is 225 minus of 184 plus 175.59 by 2. Okay, that is 45.14. Next, after that, 135 minus 88.74 plus 179.3. This is brackets. Okay, first we need to add these both values, then divide by 2 and subtract from this. Next case, 135, we need to add these two values, divide by 2 and subtract. In the same here as well. Okay, so 45.5, 45.14 and 46.015 and 65.57. okay, these are the values whatever we have got minimum midspans with respect to BC. And next, for minimum moment at midspans with respect to AB, CD for maximum midspan at BC. That is, in previous case we have taken maximum midspans for ABCD. Here we are taking minimum midspans and maximum moments at BC. So in this process, same, we will take the distribution factors, but here we have taken as minus 150, here we will take it as 90. That is minimum values with respect to AB and CD and maximum values with respect to BC. Okay, minus 90 plus 90 minus 150 plus 150 minus 90 plus 90. Then the balancing we will be doing as similarly, that is minus 22.5 minus 5.4 minus 5.4, same, and carry over, that is from this way, cross way. Okay, after this carry over, then balancing, which is minus 2.7 into 0.25 minus 11.25 plus 2.7 into 0.09, and next minus 2.7 plus 11.25 into 0.09 and into 2.7 into 0.25. After that we will sum these values, then free moments will calculate WL square by 12, that is 30 into 6 square by 12, 50 into 6 square by 12. So then we will subtract the whatever the resultant moments from the free moments. Okay, so here in this case we got the maximum moment when we consider the midspan as maximum. Okay, so is it clear? So with this we'll end the analysis process. But whereas in the problem itself we have a question, that is, analyze the beam BC for midspan positive moments. Okay, so only for midspan positive moments for the beam we have calculated. The problem, if it is not asking for beam midspan BC, then the problem continues with respect to columns and joints with respect to both conditions, that is midspan, minimum midspan and maximum midspan. Okay, for you I shall show that as well for the different problem and is solved in the next class. Okay, with this we'll end the problem whatever the question it is asked. Clear? So if we go for the process has ended here itself for our problem, because only for beams they have asked, that is we have only represented 4 beams. If they didn't ask anything specifically, then we are supposed to do for columns as joints as well. Okay, clear? Thank you.